Good day everyone. I am Nheil Patrick Patawaran, and today I will discuss to you how a SAP-1 circuit works using a circuit created by Mr. Brahma Kulkarni in the platform called Circuitverse. But before we jump right into it, let us first discuss what are the basic and primary components of the circuits. First, the program counter. The program counter is a register that holds the address of the next instruction to be executed. It automatically increments after each instruction to ensure the sequential execution of the program. Next, MAR or Memory Address Register holds the memory address of the data or instruction currently being accessed. It interfaces with the RAM to fetch the instructions or data stored at specific memory location. Next is the Random Access Memory or RAM. In the SAP-1, RAM is a temporary storage unit that holds program instructions and data during execution. It allows the CPU to read and write data dynamically, enabling flexibility and in processing tasks. Next is the instruction register or IR. It temporarily holds the current instruction fetch from memory. It allows the controller or sequencer to decode and execute the instruction. Next is the controller or sequencer. The controller or sequencer directs the operation of all other components by generating control signals. It ensures that the fetch, decode, and execute cycles are carried out in the correct sequence. Next is the accumulator or A register. Accumulator is a general-purpose register used to store the results of arithmetic or logical operation. It acts as a temporary storage for intermediate calculations. Next is the B register. The B register is a secondary register used to hold one operand for arithmetic or logical operations. It works in conjunction with the accumulator and the ALU or the arithmetic logic unit. And lastly, the output register. The output register stores the final result of computations or operations and sends it to the output devices for display. It acts as the interface between the internal circuit and the external world. Each component in the SAP-1 plays a vital role in demonstrating the principles of instruction or execution, data transfer, and basic computation. Now, let us now proceed to the explanation on how a SAP-1 circuit works in this simulation called Circuitverse. But before we jump right into it, we must first create an instruction to modify the value of the RAM. Here is the example instruction I created for the SAP-1 circuit. So the given value I chose is 9 plus 3 minus 2. So if we convert it to a instruction that a SAP-1 circuit must understand, here it is. Step 1, LDA means load. So load 8H. If you convert it into a binary, the content should be 0000 means load, 1000 means 8H. Then step 2, add or addition, add 6H. And if you convert it into a contents, it should be 0001 or means 0001 means add and 0110 means 6H. And let us proceed to subtraction, which is step 3. Subtract 5H. If you convert it into a binary, the content should be 0010 means subtract and 0101 means 5H. Next, step 4, out or output register. So if we convert it into a binary, the content should be 1110, meaning output register. And since we don't have a numerical value, the value here should be XXX or 0. And lastly, step 5, halt. And if we convert it into a binary, it should be 111111. And since we don't have a numerical value, we should just put X here or 0. So to input the given value, we should first count from 0 to 8. The first given here, or the first value in the given here, should be inputted in the 8H. So we should just count here in the address 0, 1, 2, 3, 4, 5, 6, 7, 8. So as you can see here in H, 8, we are here now in 08H. So the binary, or we should convert the 9 into a binary, and the content should be 1001. So here, now let us now plot the given plus 3 or 3. So as you can see, the additions should be plotted in the 6H address. So let's now count again: 0, 1, 2, 3, 4, 5, 6. So here we put the 3 and convert it into a binary. So the value should be, or the content should be 0011, which is equivalent to 3. And lastly, subtract minus 2. The given here should be inputted in the 5H address. So let us count again: 0, 1, 2, 3, 4, 5. So convert the 2 into a binary. So the content should be 0010. So here is the complete instruction that need to be implemented in the SAP-1 circuit. So here, as you can see, here is the instruction that is modified in the RAM in this simulation. As you can see, 00 load 8. So the first value table, or in the given earlier, is 9. So I counted from 0 to 8H. So 0, 1, 2, 3, 4, 5, 6, 7, 8. So this is where I inputted the 9 value. So again, now let's proceed to step 2. So add 6H. So the given value I chose earlier is plus 3. So let's now input the plus 3 or 3 value in the 6H address. So let's now count: 0, 1, 2, 3, 4, 5, 6. So here I inputted the 3. And lastly, the subtract step, or the step key, which is subtract 5H. And the given value I inputted earlier is 2. So I inputted the 2 value in the 5H address. So 0, 1, 2, 3, 4, 5. So that is why I inputted 0, 2 here. And E0 means binary. 14, so 1111, 0. So that's why this is E. And 0 means there's no numerical value, so 0 here. And the step 5 is FO. If we convert it into binary, is 1111, or so, which is equivalent to 15. So that is why F is written here, and 0 means there's no numerical value. So that is how I modify the RAM here in the simulation. So how does it work? When starting the simulation, the SAP-1 circuit follows the fetch, decode, execute cycle. So the first step is the program. The first execution is the program counter, and the program counter points to the address of the next instruction to be fetched from memory. Next is the MAR, or memory address register, which holds the memory address of the data or instruction currently being accessed. It interfaces with the ROM to fetch instruction or data stored at a specific memory location. And now, it will proceed to RAM, which is called random access memory. So in the SAP-1, RAM is a temporary storage unit that holds program, instructions, and data during execution. It allows the CPU to read and write data dynamically, enabling flexibility in processing tasks. So it will now proceed to the instruction register. The instruction register, or IR, temporarily holds the current instruction fetch from memory, and it allows the controller or sequencer to decode and execute the instruction. So now the cycle will now proceed to the controller or sequencer. So the controller and sequencer, of course, directs the operation of all other components by generating control signals. It ensures that the fetch or decode and execute cycles are carried out in the correct sequence. And now the cycle will now proceed to the accumulator, and the accumulator has a general purpose to register, use, or to store the results of arithmetic or logical operation, and it acts as a temporary storage for intermediate calculation. Now, the cycle will proceed to the B register. So a secondary register is used to hold one operand for arithmetic or logical operations, and it works in conjunction with the accumulator and the ALU, or arithmetic logic unit. And lastly, the output register, which stores the final result of the computation or operation and send it to the output devices for display. It acts as the interface between the internal circuit and the external world. So each component in the SAP-1 plays a vital role in demonstrating the principle, instructions, execution, data transfer, and basic computation. And that's how a simple SAP-1, or simple as possible, circuit works. Let us now simulate if the given value in the instruction will be equivalent to the result in the simulation. So as you can see here, the given, if we compute it manually, 9 plus 3 minus 2 should be equal to 10. So the value in the circuit here, in the circuit verse, or in the SAP-1 circuit here in the circuit verse, should reflect the same value in the instruction. So let us now try to simulate it. And there we go. As you can see here, the value is 0A. So if we convert A into a hexadecimal, the value should be equal to 10. So if we consider this result in this SAP-1 simulation is equal to 10, which reflects the same result in the instruction here in the given. So that's how a SAP-1 circuit works. So thank you for listening to my explanation.